4 trigonometric functions and identities. Okay, actually, equations, trigonometric equations, and identities. You guys will learn how to solve algebraic equations using your different trig functions. This is going to be a review from your previous classes when it came to doing any type of algebra-related equations with your trig identities. Okay. First, we'll start off with a few different angle relationship formulas. Remember, because sine is an even function and cosine is, because sine is an odd function and cosine is an even function, when you plug a negative angle in for sine, it will equal negative sine theta. And then cosine of negative theta will equal a positive cosine theta. All right. The next two we have talked about before. This is known as just supplementary angle relationship. Remember that the sine of pi minus theta is equal to the sine of theta. That is because when you look at an angle inside of your unit circle, from 0 to pi, the sines are the same in both the first and second quadrant. Okay, so if theta was pi over 4, then theta minus pi over 4 would be 3 pi over 4, and the sine of both of those pi over 4 and 3 pi over 4 are equal. And then the cosine of pi minus theta is equal to a negative cosine. That's because in the first quadrant, cosine is positive, but in the second quadrant, cosine is negative. All right? So if you have the supplementary angle, the cosine is going to be the negative of its corresponding supplement angle. And then the last two, sine of pi over 2 minus theta is equal to a cosine of theta. And then the cosine of pi over 2 minus theta is equal to sine theta. All right, a few different angle relationships, so then that way when you see these inside problems, you can rewrite them using those respective formulas. Your Pythagorean identities. You have your very first one, which is what? We talked about it last week. What's the first Pythagorean identity?
Cosine squared plus sine squared equals 1.
Okay, let's make sure that we don't forget about our thetas. Okay, so cosine squared theta plus sine squared theta is equal to 1. Okay, these other two are derived from this very first one. If I were to divide every single term by cosine squared theta, what's cosine squared theta divided by cosine squared theta? 1. What's sine squared theta over cosine squared theta? Tangent squared theta. And then what's 1 over cosine squared theta? Secant. And that's how you get the very first Pythagorean identity that you see on the board. You can get the next one by doing the exact same thing, except dividing every single one by a sine squared theta. And then that's how you get to the other ones. Okay? So these are a few other Pythagorean identities that you can also use to add in to when you are solving algebraically some of the trig equations that you'll come across. All right. So let's practice some simplifying. Do realize that the Pythagorean identities can also be rewritten, okay? So this is also the same thing as saying 1 equals secant squared theta minus tangent squared theta, okay? Do realize that every single one of these Pythagorean identities can be written in different ways, and I'll fix it. All right? Let's take a look at these first two. Asking you to simplify sine x plus cosine x squared. Okay, how would I simplify this? You would have to FOIL it. Remember, the square means that you're going to multiply it by itself, so that's sine x plus cosine x times sine x plus cosine x. So when you FOIL, that becomes a Okay, please make sure that you guys are including your variables. If you leave out the variable, that is incorrect. Okay, so please make sure that y'all also saying it, because some of you guys will leave that out in your work, and then you'll be solving for nothing because you don't have a variable there. Okay? How can I continue to simplify this?
Take out a sine squared theta and a cosine squared theta and replace it with 1.
Okay, well I can't really take it out. I can replace them with a 1, and then what can I do here?
Combine the terms.
Okay? This too is another identity that we'll talk about later today, but for the moment this will suffice. It is a double angle identity. You guys try the second one. How do we simplify this one? What part? The denominator turns into what? Yes, the whole thing turns into secant, because that is that first Pythagorean identity. So it turns into secant squared. So my denominator becomes secant squared x. And that was in that parentheses, turns into cosecant squared x. Do I do anything with the tangent?
You can eventually turn it into sine squared x over cosine squared x.
Are you going to change the other ones into that as well?
Yes.
Okay. So then tangent squared x becomes sine squared x over cosine squared x. What does cosecant turn into? 1 over sine squared x. And then what does secant squared x turn into? Those identities, these are your reciprocal identities. Okay? We talked about those last week as well. Cosecant, the reciprocal of that is 1 over sine, or sine and cosecant, they're reciprocals of each other. Secant and cosine, they're reciprocals of each other. And then, of course, tangent can be written as sine squared x over cosine squared x. Keep simplifying. Your sine squares cancel out. Now, if you notice, once you cancel that out, you have 1 over cosine squared x all over 1 over cosine squared x. When you have the same thing being divided, that becomes 1. So all of that simplifies down to be 1. Questions on simplifying? Okay, these are just 2 examples. You could be asked to simplify several other things using any of the other identities as well. Okay? You could also be asked to factorize. Okay? So your old skills of factoring, all of your skills from factoring just regular polynomial equations, they're going to come into play here as well when you're doing trig. Okay, so you can't forget how to factor either. When you look at that very first one, you have cosine squared x minus sine squared x. This one models what factoring concept? What old school factoring concept does this model? The difference of squares. Okay, when you had a squared minus b squared, that could be factored to what? Okay, what about this? X squared minus 4. How do you factor that? X plus 2x minus 2. So that's just a plus b, a minus b. This is set up in the same format. So if that's the case, then this factors down to be what? Cosine what? Cosine x plus sine x. And then? And you can't go any further from that, because cosine x plus sine x does not turn into 1. They has to be square in order for it to turn into 1. So that's about as far as you can go up to this point. Of course, you can be asked to do several things from here, but knowing how to factor that, that's very important. What about B? It is, this one's one of the quadratics, okay? Such as a squared minus 3a plus 2. If you can factor this, you'll be able to factor the tangent one. How do I factor something like this? Okay? To factor, not to solve. To factor. Okay, now be careful. Our variable is x, so it would be tangent x minus 2, and then tangent x minus 1. Okay, so you're looking for two numbers that multiply to give you your C, add together to give you your B. Okay, so don't forget about those skills as well. All right, try simplifying these. So in A, hopefully you notice that you could take out a 2 from your numerator, leaving you with a 1 minus cosine squared x all over 1 plus cosine x. Okay, now that's not really simplifying, but inside of the parentheses, that's another difference of 2 squares. That can be factored down to be 1 minus cosine x times 1 plus cosine x. And when you factor this way, you will see that your 1 plus cosine x cancels out. So then you're left with 2 times 1 minus cosine x. It's the same thing as saying 2 minus 2 cosine.
If you don't distribute the 2, then is that
Then in B, again, the denominator is just like the one that we had before, so this 2 can be factored into difference of perfect squares. So then the denominator factors to be cosine x plus sine x, and then cosine x minus sine x. So then the top and the bottom cancel out as well, and you're left with 1 over cosine x plus sine x. And you can't go any further from here. Questions? We'll come back to that one. All right. Double angle identities. Okay. Double angle identities. There are a few other identities that can be used when simplifying, also with solving different equations. Sine 2 theta, that 2 is a normal size 2. It is on the same line as the sine and the theta. It's not being squared. That double angle identity is 2 sine theta cosine theta. Cosine 2 theta does have 3 different ones. Depending on the problem, one of the identities may be better to use than the other. It really is, again, going to depend on what you're given, or what you already have in the problem that you're dealing with, which double angle identity you're going to use for cosine, but those are the 3 there. And then tangent 2 theta, as you can see, only has the 1. All right? So we are asked to find each of the double angles, given that sine is 3/5 and cosine is -4/5. Okay? Now we can easily work this out. Since we're given both sine and cosine x, to find sine of 2x. The identity says 2 sine theta cosine theta. Well, we're going to replace theta with an x because that is our variable here. So then it's going to be 2 sine x cosine x. And all we do is literally replace sine x with the value 3/5. We don't plug 3/5 in for x. That is exactly what sine x is equal to. It's equal to 3/5. So we replace sine x with 3/5, cosine x with a -4/5, And then we multiply from there to find the value, the exact value of sine 2x. What is that? So negative 24 over 25 is the sine of 2x. For B, we're asked to find the cosine of 2x. We have three different identities that we can use for the double angle for cosine. So really and truly, it's more so, and we actually have the value of sine x and cosine x in this problem. So we really could use any one of the three. It really doesn't matter which one do you want to use. Okay, if I use the second one, then which is 1 minus 2 sine squared x, because again, theta is getting replaced with an x. Remember, sine squared x is the same thing as saying sine x, the quantity, squared. So then I can replace sine with 3/5, and then I square that. Order of operations says I square first, so what's 3/5 squared? 9 over 25. Then I multiply that by 2. What's 9 over 25 times 2? So this becomes 1 minus 18 over 25. So cosine of 2x is going to be equal to 7 over 25. And that's the same value you would get if you use a different identity as well. Last but not least, we have tangent 2x. Tangent 2x, we have the identity there. Remember, tangent x is the same thing as saying what over what? Sine over cosine. So we have a sine x, we have a cosine x, so we need to figure out what tangent x is going to be. So that's going to be nothing but sine x over cosine x. So when I keep change flip, what is tangent x? Negative 3 over 4. So then that's exactly what I plug into my identity. 2 times negative 3 over 4, all over 1 minus negative 3 over 4 squared. That becomes negative 6 over 4, all over 9/16, 7/16. I believe. 16 minus 9, 7. Then I'll have to keep change flip. And what is tangent 2x? Negative what? 24 over 7? We could also obtain that by doing sine of 2x divided by the cosine of 2x. And that will give us tangent 2x. That also works as well. But again, depending on what you have, what you had to find, at least this way we based it off of what we were originally given, because there could have been potential that we got sine 2x and cosine 2x wrong. All right? Questions on using double angle identities? All right. If theta is acute and cosine 2 theta is equal to 3/4, we want to find the exact value of cosine theta and sine theta. Okay? You've seen this terminology before. If theta is acute, if it's acute, it's in the first quadrant, which means the sine and cosine in the first quadrant are both what? Positive. Okay? Hand back your homework, you're going to see that some of you guys made a mistake on that particular question that had that in there. All right? If it said that theta was obtuse, it will be in the second quadrant. In the second quadrant, cosine is what? Negative. So you got to keep that in mind too. They don't just say that arbitrarily. It's saying that to let you know the value of each of these, okay? So we know that sine 2 theta is equal to 3/4. We have three different identities for sine 2 theta. Which identity do you want to use? I would suggest either the second one or the third one, because the second one's going to help you find sine first. The third one's going to help you find cosine first. We got to find both eventually. So the first one I heard was the last one, so let's use that one, which was 2 cosine squared theta minus 1. I'm going to use that to replace my double angle identity. And from there, it becomes algebra to solve for cosine theta. How do I start? What's 3/4 plus 1? What's 7/4 divided by 2? How do I solve for cosines? Square root. And remember, when you square root an equation, it's always plus or minus, but because we're in the first quadrant, we know it's going to have to be a positive. Now, can I take the square root of 7? So the top becomes the square root of 7, but the bottom becomes what? 2 square root of 2, because the square root of 8 simplifies down to be 2 square root of 2. Can I leave it like that? You know you can't leave that like that. You cannot have a radical in the denominator. So we have to rationalize. Multiply your top by 2 and your bottom by 2. So then cosine theta is square root of 14 all over 4. Now to find sine theta, I can either use the double angle identity for cosine 2 theta, or I could use what other identity? Use Pythagorean identity. The only downside I would say about using Pythagorean identity is because what if you did cosine wrong? Now you have no chance of getting sine right. Okay? So keep that in mind. Okay? Keep that in mind as you're doing these different problems. I am going to use the double angle for cosine 2 theta, even though I know we found the correct cosine. We did find the correct cosine, right? Yes, we did find the correct cosine. Okay? But just in case. All right? Subtract 1 from both sides. What's 3/4 minus 1? Negative 1/4. Divide both sides by a negative 2. What's negative 1/4 divided by negative 2? Then I'll have to what? And we know it's going to be positive or negative? Positive. Very good. That's 1 over 2 square root of 2, which I cannot have. So once I rationalize, sine theta is what? Use double angle identities to find exact values. Questions? You can also use double angle identities to simplify as well. This would be helpful, like maybe a first part of another problem where you actually might have to solve an equation. Say 3 sine x cosine s was equal to the square root of 3, and they asked you to solve. Being able to use your double angle identities to simplify that 3 sine x cosine x will help you in solving the problem. Which one does this look like? Sine what? Sine 2 theta is equal to 2 sine theta cosine theta. But there's a difference between the double angle identity and what we have. What's the first thing that you notice? It's a 3 instead of a 2. Okay? That means that the front of my double angle identity is affected in some way. What else do you notice? Your variables are different, which means you're not going to have a theta anymore, you'll have an x, okay? And I boxed these areas because those are what's going to be affected. I'm trying to simplify it down into a simplified form of this double angle, okay? So as we already can see in the pink, theta needs to be replaced with an x. do need to do something with that 3, but I don't know what you mean when you say pull it out.
Like, can you make that sine 3x?
No, because the 3 is on the outside, so it's basically like 3 times sine x. It's not inside with the variable. 2/3? Not 2/3. 3 halves. Yes. If I do 3 halves, that's going to turn this 2 into a 3, and so then this would be our simplified form. Okay? You have to ask yourself, what do I multiply the front of this by so that I can adjust this 2 to turn it into a 3? And that would be 3 halves. Very good. What about this next one? Well, what identity? Which one of the cosine 2 thetas?
2 cosine squared theta minus 1.
Okay? So there's a big difference between with what we're working with here. Okay? It's a big difference. Yes, there's a variable difference. Okay, there's actually a couple of things. Let me hold off on my boxing, because I want to see if anybody notices something first before we go forward.
Everything's multiplied by 2. Looks like it.
So could I take out a 2? Like if I take out a 2, what does that give me? It still says a 2b. That pulling out 2 does not affect that 2b on the inside, but it does affect this 2 here, and it becomes a -1. Okay? So if anything, technically, this is still the same, is it not? Like essentially, those are still the same if I look at just the inside of the parentheses. But theta has changed, hasn't it? What has theta changed into? It's a 2b. There's a 2 in there now. Okay? So the theta is going to be replaced with a 2b. And since I did factor out a 2 at the very beginning, what does that mean for the beginning of this? I do have to multiply by 2, because technically you have this. So then that becomes 2 cosine 4. Questions? Compound angle identities. Back in pre-cal, they were known as your sum and difference identities. That's why I put in parentheses, maybe to trigger your memory for those of you all to pre-cal. Okay, these are your different compound angle identities. These are used when you actually have 2 angles that are being added together, A and B, or being subtracted from each other and asking you to take the cosine. That's why you can't distribute the cosine into that parenthesis, because it's a whole nother identity in itself. Okay? And in the reference booklet, it is written this way. It is written this way, so you want to be careful on how you are reading it. Okay? The symbol of the plus and minus on the inside, like it corresponds to that respective order. So cosine of A plus B is equal to cosine of A, cosine of B minus sine A, sine B. But when it is cosine A minus B, it's cosine A, cosine B plus sine A, sine B. Does everybody see how the symbols go? Like the stacking kind of shows you, it goes with which one. All right? When I look at this problem, it's asking me to expand and simplify sine of 270 degrees plus alpha. Okay, that's the alpha symbol. Here, I want to use your compound angle identities because it's asking you to add two angles together. So that means I'm going to need to use the compound identity of sine A cosine B plus cosine A sine B. Okay, 270 relates to A, alpha relates to B, and you just use the expansion of the formula. So that becomes the sine of 270 degrees, cosine of alpha, plus, because again, how the symbols are set up, plus goes with plus when it comes to sine, cosine A, sine B. So cosine 270, sine alpha. Now as you use circle, what's the sine of 270 degrees? That becomes -1 times the cosine of alpha plus what's cosine of 270? 0 times sine alpha. So when I simplify this, my final answer is just going to be negative cosine alpha. Of course, this can be equal to a number, and then you will continue to solve from there. Questions? What about this? You're asked to simplify. What does this look like? Cosine compound angle. Okay. Well, in cosine, I have cosine. I have an A plus B, and I have an A minus B. Which one is it? How do you know it's A plus B? Because the signs are the opposite. So what's A in this problem? 3x. What's B? So then when it asks you to simplify, you basically have this entire expansion. They want it in the nice, neat package. So this becomes the cosine of 3x plus x, which is what? So cosine 4x. And that's your answer. Now remember, A and B represent what? Two angles being added together or two angles being subtracted from each other. Okay? So if you're asked to show or find the exact value of something like this, sine of 75 is equal to the square root of 6 plus the square root of 2 over 4. Is 75 on your unit circle? No. But aren't there two angles on your unit circle that can add together to give you 75 or subtract it from each other to give you 75? You can definitely use those too. So go ahead and show, using your compound angle identities, that the sine of 75 is the square root of 6 plus the square root of 2 over 4. Doesn't matter what two angles you use as long as they actually add to give you 75 or they subtract to give you 75 and they're on your unit circle. That's the only way this is going to work. So if you use 30 and 45, that definitely works. When you're adding them together, that means I need to use the sum one of the compound angles. So that becomes the sine of 30 cosine of 45 plus the cosine of 30 times the sine of 45. And then again, you use your knowledge of your unit circle to find your angles. The sine of 30 degrees is? The cosine of 45 degrees is? The cosine of 30 degrees is? And the sine of 45 degrees is? And then you multiply, it becomes the square root of 2 over 4 plus the square root of 6 over 4. And of course, if they have the same denominator, you can put them over the same one, okay? And so that is how we get the square root of 6 plus the square root of 2 all over 4. Remember that notation? Remember, any of your show problems, you can put QED or you could put LHS, the 3 bars, RHS. Y'all remember that from like unit 1? Okay, don't forget at the end. Questions on compound angles? Okay. Let's take a look at this one. Give you guys a few minutes to see if you can figure out how to tackle this one. Suppose that sine x minus the square root of 3 cosine x is equal to k cosine x plus b. K is greater than 0 and b is in between 0 and 2 pi. You have to find the value of k and b. I want you to take a few minutes, see if you guys can figure out a starting place, then I'll see where you are. Cosine? Okay, I can definitely take this part right here and I can use that expansion, right? So that becomes cosine b, then sine x, sine b. What's in between them? A minus, because that is a plus up there. What happens to that k? It's on the outside of this whole thing, which means I could do what with it? I could distribute it, okay? Okay, good starting point so far. What can I do from here? Remember, this is supposed to equal sine x minus square root of 3 cosine x. Make the sine, you said multiply by -1 and make the sine x part equal.
Like,
keep going. I think you're on it.
Like make the sine k sine x sine b equal to sine x, and like k cosine x cosine b equal to root 3 cosine x.
This part is supposed to equal this part, because that's where the sine x is, right? And then this part here is supposed to equal this part. Keep going. Yes. So what can I do from here? Because they're supposed to equal each other. The parts in the purple, the parts in the orange are supposed to equal each other. Okay, well if I do that, that gives me a negative square root of 3 equals k cosine b.
Negative sine b equals like 1, right? Because if you divide this side by sine x, and you get 1.
Okay, so this becomes 1 equals negative k sine b. Okay. Now what? Can I what? Divide by negative k? And then what?
Find something on the circle.
Okay. Yep. The only problem is that I got a k. I got a variable. And there's no 1 over negative k anywhere on the unit circle.
Can you solve for k and plug it into the other equation?
Like a system? Because I have 2 equations, 2 different variables, right? Sure can. Which one you want to solve for? I'm going to solve for k. That'll probably be the easiest thing to do. Which equation should I solve for k in?
1.
This one here? Okay. So if I do that, this becomes 1 over sine b equals negative k. So then k is going to equal a 1 over sine b. So then I can plug that in over here. This gives me a negative square root of 3 equals a negative 1 over sine b times a cosine b. What does that become? It does become cotangent because that becomes cosine B over sine B, which is cotangent B, but it's going to be a negative. So negative cotangent B equals a negative root 3 cotangents. Can I just say this is square root 3 equals cotangent B, since they both have a negative? Maybe make it a little easier on yourself. I mean, I don't know if it will. Turn that into tangent. What happens to that? 1 over root 3, which is, where's tangent root 3 over 3? I think you might know the tangents better. Huh? And 7 pi over 6. Okay? So right now we have b equals pi over 6 and 7 pi over 6. They both fall between 0 and 2 pi, but now I got to find k so that k is greater than 0. Don't forget about those restrictions up there. So if I plug in pi over 6, this becomes a negative 1 over sine pi over 6. What's the sine of pi over 6? Or what's sine of pi over 6? And what's a negative 1 divided by 1/2? Can k equal a negative 2? What? No. So that means that b can't be pi over 6 because k has to be a positive number. And if pi over 6 is be a negative k, it can't be that one. So it's going to have to be 7 pi over 6 because what's 1 over negative sine of 7 pi over 6? Or actually it's a negative, but whatever. A negative make a? And what's 1 over 1/2? Whew. Questions? Questions on using your identities? Take a look at these two. Try to work these two out. Remember, in these types of problems, when we're trying to prove something, we work with one side to make it to look like the other side. And since we were given this hint that we need to use the identity to do that, it would have been easier, if anything, to start with this side and try to make it look like the other side. This is the half angle identity for cosine. Pre-cal folks, it might have looked familiar from your journeys last year. But the thing is, what we can actually do here is that we can do kind of what we did with like those problems when we were using the double angle identity to rewrite one. We can do that here. All right, so this 1/2 affects what part of this? It affects the cosine 2 theta or just the theta itself? It affects just the theta, okay? So then that's affected. So then that becomes cosine 2 1/2 x equals 2 cosine squared 1/2 x minus 1. And so from here, what we can do is, from here, we can solve now for the cosine 1/2 x over there. All right? And so, what's 2 times 1/2? So this becomes cosine x equals 2 cosine squared 1/2 x minus 1. And then I can continue to add 1 from here. Then divide by 2. And then take the square root. Okay, remember when we take the square root, it does become a plus or minus, but it becomes the plus version because of what part? Because of that domain part here, where it says that x has to be in between 0 and pi. And the thing is, that's with respect to x. This isn't x, though. This is a, what x? It's a 1/2 x. So that means this domain is going to be affected by the fact that there's a 1/2 there, which means that it's going to be from 0, because, you take 1/2 of 0, it's still 0. But this one's going to become a pi over 2. And cosine in the first quadrant is what? Positive. So cosine 1/2 x is equal to a positive square root of 1 plus cosine x over 2. To find a similar expression, did not mean to do that. To find a similar expression, what could I do? Not 2 sine theta cosine theta. We want to still stay in the double angle for cosine.
Would we use the other one?
Which one?
The 1 minus 2 sine squared theta.
How could I use this? Plug in the 1/2 for the theta. The 1/2 x? Where at? If I do it that one, I gotta do this one too, don't I? And I continue to work it out, right? The same way we did before. By subtracting 1. Dividing by -2. What happens when I divide by a -2? What happens when I divide by a -2? Isn't just the denominator that's negative. So that means the cosine's going to be, It's a +1, and then a minus cosine. The 2 is the positive, so now I'm taking care of the fact that I've divided by a negative. I've changed the signs of everything. And then I'll have to what? And this is going to be positive or negative? Positive. And this is the double angle identity for sine. Not double angle, I'm sorry, half angle identity for sine. So just to recap, you have your compound angle identities. These are used to simplify. They're also used for solving, which we'll talk some more about on Thursday. You have your double angle identities, which again can be used to find exact values, as well as for solving, simplifying, rewriting expressions in terms of other things. Don't forget about factoring and your basic skills of simplifying, foiling, etc., with your other more basic identities when it comes to dealing with your trig expressions and your identities.